Are you one of those people who sat in maths class and wondered, when will this stuff ever be useful? Well, your long wait is finally over. We're at the 17th meeting of the Maths in Industry Study Group right here at the University of Zululand in South Africa to discover how real-world problems are being solved with mathematics.
In 1984, an eruption of a lake in Cameroon killed 37 people. And just 2 years later, a second lake erupted, killing 1,746 people and over 3,500 livestock in nearby villages. You might be wondering how a lake can erupt and with such devastating consequences. But you're probably also wondering when the same thing could happen again to another lake. So today, as part of the Maths in Industry Study Group, we're looking at these incredible circumstances and asking whether mathematics can shed any light onto some of these questions. So I'd like to introduce you to a number of guests. The first, Keegan Anderson. He is a lecturer at the University of Johannesburg and with a research focus in applied and computational mathematics. Keegan, when we think of these lakes, we think of peaceful spaces. Tell us what hidden dangers are lurking beneath the surface of Lake Kivu in particular.
Thank you for having me on the podcast. And Lake Kivu, unfortunately, is one of 3 lakes in Africa which experience limnic eruptions. Now, these eruptions are due to gas which gets trapped at the bottom of these lakes. As you mentioned, there were 2 other lakes as well in which these eruptions already occurred previously. And Lake Kivu, in that sense, is sort of the geological version of a pressure cooker. And what especially makes it dangerous is that Lake Nyos, which you mentioned, which 1,756 people died, is about 2,000 times smaller than Lake Kivu. So the consequences of a limnic eruption in Lake Kivu is going to be on a much larger scale.
So let's try and understand this a little bit better. Why do these lakes exhibit this phenomenon?
So these lakes are peculiar in the aspect that there are 3 lakes in the world in which gas bubbles up from the bottom of the lake due to nearby volcanic activity. Now, you would ask the question, why doesn't this gas just bubble up through the lake and disappear? In Lake Kivu's instance, the gas is quite deep, almost 485 meters at maximum depth, and that causes stratification in the lake. And this sort of keeps the gas trapped inside Lake Kivu and the other 2 lakes as well. And this sort of, with all the water in the lake, it creates a lot of pressure. And there's a lot of mathematics involved, but one can show that the bubbles which you think should form are not there. They're infinitely small almost.
So this is a bit like a Coca-Cola that stays closed, and the gas bubbles are actually dissolved in the liquid.
Exactly.
At the higher pressure.
And just like with a Coke bottle, where if you shake it up and you release the top and it erupts, this is sort of what we think happens in these lakes.
You spoke a little bit about stratified lakes. So you're saying that the water in these lakes actually has different properties at different depths?
Yeah, that has been seen from geographical surveys and such, and profiles of the pressure and temperature gradients, where there seems to be a clear distinction in changes in temperature. So it's not linear, it doesn't go down smooth and so. It seems that at certain levels in the lake, there's a jump in pressure and temperature and such, which indicates this stratification. So unlike a Coke bottle where the fluid is all exactly the same, you can sort of think of mixing Coke and water, and the water stays on one level and the Coke just sort of floats on top on top of the water.
What gases are we talking about that are coming through from these? And when they do find their way to the surface, what is the impact of that?
In Lake Kivu's instance, the gases are carbon dioxide and methane. And now, carbon dioxide tends to be more soluble than methane, I suspect. I'm unfortunately not a chemist, so don't quote me on that. But the methane has a bigger probability of forming bubbles if it gets above the stratification, and that bubbles up. The carbon dioxide, not so much. But the problem is the carbon dioxide is the killer gas because it's more dense than air. So if an eruption happens due to the methane erupting or pressure buildup or such from the methane, it releases a carbon dioxide cloud, which then eventually filters down. If there's anything below the lake, that sort of just filters down and stays close to the surface.
And that's what caused the deaths in 1984 and 86.
Correct, yes.
So asphyxiation from carbon dioxide that had emerged from the bottom of the lake.
Yes.
So where is Lake Kivu, and who utilizes the lake?
So Lake Kivu is situated on the border between Rwanda and the Democratic Republic of Congo. And in my research about this matter, we saw that it is mostly rural communities which are situated on the lake shores due to a biozone layer which is part of the lake. The biozone layer, of course, providing fauna, fishes, that kind of thing. So these rural communities, basically sustenance fish and commercial fish. That's their main form of income.
And is there any other use of the lake? Are there any industrial uses?
Indeed, there is. Due to the nature of the lake with methane coming in from the bottom, some industries seem to be forming on the Rwandan side to try and extract this methane for electricity generation.
How did this problem come to the Maths and Industry Study Group?
We were originally approached by Dr. Dennis Ndanguza from the University of Rwanda with this problem to gain a better understanding of the mechanisms which drive the lake. In my research 2 years ago, when we originally tackled the problem, it appears that up till this point, it's mostly been economic, geological, and geographical studies which have been done about the lake. There isn't anything in the literature pertaining to the physical mechanisms of the lake, so to speak.
So tell me a little bit more about the layers in this lake. What are the consequences of these different layers?
So there seems to be three main layers. The deepest layer is where all the methane and carbon dioxide seems to be trapped. Then you have an intermediate layer, and at the top of the lake there is a biozone layer which contains fishes and all that, which is important. The biozone layer is important to the communities living on the lake. The methane extraction is done from the bottommost layer of the lake.
So these distinct layers, what would happen if they were to start getting mixed up with one another?
If it becomes very turbulent, that bio layer might grow. And if the concentration of things remain the same, but you have a growth in layer, it might upset the ecosystem. The eruptions would occur if there's a mixing or an eruption from the bottommost layer. But if the topmost layer, the biozone, gets destroyed, local communities might die out because, as I mentioned, they fish these layers for sustenance and commercial purposes.
It sounds like there's a problem that's potentially waiting to happen, and we're looking for some solutions. We're speaking to Dr. Osman Nooraldeen. Osman is at the University of KwaZulu-Natal and a specialist in applied maths and especially fluid mechanics. Osman, what process did you go through to solve this problem using mathematics?
Okay, thank you very much for having us. So we firstly look at the information that we got it from the Lake Kivu, And this lake is quite stratified lake with several gradients of layers. And so we look firstly, we look for main key factors that determine the density of the water. So we look at maybe the temperature and the concentration of the dissolved gas and the pressure and the depth of the layers and the velocity, and the turbulence kinematic energy also can come in that point. So to model the turbulence in the lake.
So what was the model you decided to use for looking at the turbulence in the lake?
Okay, so based off these factors, we can think about mathematical model that describe the fluid motion in the lake, and that will come the Navier-Stokes equations. Basically, the Navier-Stokes equation are just a second Newton law that's applied to the fluid, and also the conservation of mass, if the mass is conserved, and the turbulence kinematic energy, and the heat equations that distribute the heat in the lake.
So just to understand a little bit better, what is a mathematical model, and why do we make mathematical models?
Well, mathematical model is a language that we use to describe the world and the universe. And the mathematical model, that's something we can describe how things behave for long terms and under certain conditions. Also, mathematical models can predict the future if you have data available for such model.
And so what are the factors that you used to create the model for Lake Kivu?
So those are the factors are the temperature and the concentration of the dissolved gas, and also the depth of the gas is important for us, and the velocity of the wings, wind stress, and the turbulence kinematic energies.
Okay, and based on these physical properties and certain fundamental physical laws, and I think you mentioned Newton's second law.
Yes.
You can make predictions about what could happen at the boundary between these different layers as a result of this turbulence.
Yes.
Okay, so I'd like to find out, once you've developed such a model, how do you test and get ideas and predictions out of such a model? So we're going to talk to Samantha Carey-Fourie, who's a postgrad student at Stellenbosch University, and she specializes in applied maths and fluid dynamics. Samantha Carey, how do you know if your model is correct?
Well, what you do is it's more like you validate the model. So you have a very simple basis model that you start off with. So the Newton's second law, conservation of mass, and you have a very simple model. So you add in factors and terms and constants. So we looked at the density of the lake and the actual length and width of the lake. So you add those to the lake to model it for your specific lake. Then you look at data that has been recorded previously by other researchers, and you look and you test your model and to see if it performs and gives the same outputs that were shown and recorded. So that's how you test it and validate that your model is correct. Yeah.
Okay. And where is some of that information coming from?
So we did a lot of research and reading more articles that have been redone in the past few years. Especially there's one done by Wits University. So this is mostly just about reading and Googling and looking up, seeing if we can find terms and constants and equations to see if we can apply these to our specific model.
And once one is able to make some kind of a prediction with this, what does one then go and do with that information?
The predictions can be used to make better decisions, fiscal decisions, policy decisions if you're looking at country level, better economic decisions for communities or states or such. In the case of Lake Kivu, it might also be used to make better arrangements should a limnic eruption occur somewhere in the future. It might help the communities prepare, or the government prepare for such an event. in the face of both the instability in the area and global climate change.
Yeah, also, like after we got a model and we have a precise model for the lake that describe the turbulence in the lake, then we can easily, the policymakers can decide based on that precise model we formulated.
Yeah, I guess it's also a case of sustainability. If something happens to disturb the biozone, it might influence the fish populations or such. And since humanity is sort of increasing population sizes, you want a balance between the local ecology and the people staying on the lake. Any force, external or internal, which causes an imbalance will be detrimental.
So it sounds like there's some pretty powerful insight and value that can be added by bringing mathematics to this problem to try and understand it a little bit better. I'd like to ask you to reflect on the experience of being part of the mathematics and industry study group over the last couple of days. How was this experience for you? Did you find it useful and did you find it challenging?
Oh, definitely. I always enjoy. It's not my first time at this study group. I've been here previously. I do enjoy the challenges presented every year, and it's quite a learning experience for me as well.
Yeah, it's. This year's my first year coming here, so it's quite cool to come from an academic where I've only done simple problems and to actually go and see what it's like in the industry, where companies will be presented problems for us to model, which is more about learning how to model, learning from more experienced people like my colleagues over here. So it's very cool and very fun.
It's a different experience as compared to what you get at university, because at university you sort of taught these idealistic models. So this is for a lot of students their first exposure to actual real applications of mathematics which affect real world things.
Yeah, it's a quite interesting experience that we have in mathematics and industry group. So you come out from the academics and you will find some real world problem that present by the industries, and then we try to get a deeper understanding of the mass that behind these real world problems. And then also one advantage that you can get interacting with different people with having different idea, different thinking, so that a problem can be tackled on that.
Did you have any big aha moments or moments of discovery or realization in the last few days?
If we have one, I'll let you know. We're still working on that, I guess. But we did have a mini aha moment earlier with some of the students. We were working on a set of equations and trying to model them on the computer, because that's where in applied mathematics, most of your number crunching happens. It's sort of the applied mathematician's lab. And the resulting graphic which we obtained conforms to what we would expect would happen in the lake. Like I mentioned earlier, if there's turbulence, it might cause this biozone layer to grow. And just from what we did a bit earlier today, we saw that for this depth of the lake layer.
Okay, fantastic. And how does this experience affect your approach to research?
For me personally, it has completely blown open the world of research. I had a sort of isolating experience during my postgraduate studies. So for me, it was quite wonderful to come out and see how other people approach problems and approach research methodology and the steps they take. It just gave me it was quite inspirational, I must say.
Yeah, it's lots of people from different backgrounds. So you learn a lot about, not every university teaches the same thing. So a lot of them focus on different areas. And when you work in a group, it's not just people with fluid dynamics. It's other people who just thought the problem was very interesting and thought they could apply what they learned, studying a completely different degree. And it's very interesting.
For me, it's just also the same as like my colleagues mentioned, that you come with different people and different thinking also, and also like for future collaborations, networking with people that are close or related with your areas of interest. Also the group, all the people in the group are not just like a fluid dynamic or mathematical model. They are different type of applied mathematician that they can come in, and so you have a chat with them and then for future collaborations.
So my interest is in research communications and how researchers communicate with various audiences. Do you think that you can improve communication skills and foster research communications through experiences like this?
Yes, well, you can improve your research experience communication with, because we have many experts also in terms of like top applied mathematician coming to the industry and applied mathematics groups, and so you can easily improve.
Yeah, so we do presentations almost every day, which is more like report backs. So you learn how to interact with people in the crowd, and especially with people answering questions about you learn how to communicate it to people who haven't been working on this problem for a few weeks. So it's how to not simplify it, but break it down in easier terms to understand. And you learn how to communicate that by doing also reports that we give back to the MSIG.
Part of this communication, of course, during the study group this week is with the industry representatives. And they might not have the necessary mathematical background. So you have to find a way to communicate your results back to them without making it too technical, which is a challenge in and of itself sometimes.
I remember that lake erupting when I was a child, and it's been fascinating to talk to you about this new collaboration, bringing people together from different disciplines to try and understand what was happening there, and potentially to be able to influence the future in some way in terms of safeguarding people and their livelihoods. So it's really been fantastic to hear from you. I'm grateful for all of your contributions, and we really look forward to hearing more about what you uncover in the next couple of days.
Thank you.
Yeah, thank you. Yeah.
The South African Mathematics and Industry Study Group was founded by Professor David Mason in 2004 at Wits University and has created exciting opportunities for collaboration between mathematics researchers and industries facing complex problems. The 2020 event is hosted at the University of Zululand and is supported by the DSI NRF Center of Excellence in Mathematical and Statistical Sciences, the Herman Althover Trust, and the African Institute for Mathematical Sciences. This podcast was sponsored by the Center of Excellence in Mathematical and Statistical Sciences, an initiative of the Department of Science and Innovation and the National Research Foundation.